In this video, we're going to answer the question, why atoms bond? And so as the notes state, you can kind of memorize that atoms bond to achieve a lower energy state, or perhaps even the lowest energy state possible. If we go back to Unit 2, when we learned about spontaneous and non-spontaneous processes, you may remember this kind of picture where I drew a hill and we said, okay, if the ball is on the top of the hill, we would agree that the ball can naturally, on its own, just roll down the hill to achieve a lower energy state. This happens without any external force, and so we call this a spontaneous process or a thermodynamically favorable process. On the flip side, we could have a ball at the bottom of the hill, and we said the ball can certainly roll up the hill, but it's not going to happen on its own. And so for the ball to roll up the hill, it requires an external input of energy. Because it requires an external input of energy, we would call this a non-spontaneous process. And that non-spontaneous process means that it's a thermodynamically unfavorable process, which means it doesn't happen on its own. So let's talk about like molecules. Instead of an entire process happening, which is what we discussed in Unit 2, and we will certainly discuss later in second semester, let's discuss why do molecules even form from atoms bonding. So if we look at this graph, we have our distance on the x-axis, and we have potential energy on the y-axis. And for this set of notes, you can just think about your y-axis as being just energy. We could have a situation where we have atom A, and let's imagine a scenario where atom A is known to form bonds with atom B. One of the key postulates of kinetic molecular theory is that if atoms are going to bond, they must collide with each other. Well, in this scenario, A and B have quite a large distance between them, and so what I would argue is that while they can form a bond, they don't form a bond unless they're close together. So in this case, these guys are too much distance, or they have too much distance to form a bond. As a result, we can see that their energy value, or their Y value for this kind of distance, is essentially 0. They're too far apart. Another scenario could be if we have atom A, and it is so close to atom B, perhaps even close to overlapping. Well, because the outside of an atom is composed of the electron cloud, and only some of the electrons are involved in bonding, it's actually quite unstable for two atoms to be too close together. We want their valence electrons to be close so that they can form what's called a covalent bond, where they share electrons, or perhaps an ionic bond where they transfer electrons. But truly, we just want that to occur with the valence electrons and not the core electrons. So in this scenario, A and B are too close. And as a result, this is unstable. And a good rule of thumb in the chemistry world is that an unstable situation is a situation that has a higher energy value than just baseline. And because it's unstable, like I just said, there's too much energy. And if atoms bond to achieve a lower energy state possible, this is why A and B are not going to bond in this manner where they're too close together, because they're not forming a lower energy state. And as the graph suggests, actually their energy value is higher. And so if we would like to use this graph to find the ideal distance between atom A and atom B, we want to find the trough, or the bottom of this curve. And this is what we would consider the ideal bond distance, or what I'm going to call the ideal bond length. In this scenario, atom A and atom B are close enough together. They are close enough together that they can form attractions with each other, but they're not too close together where their core electrons actually cause too much repulsion. And so this distance between the nucleus of A and B is actually defined as the bond length. So in this scenario, that ideal bond length would be maybe something like 3.7. Whatever these units are, oftentimes the units might be measured in like nanometers, but they don't have to be. So as we keep working, let's work on two types of compounds. The first is what's called an ionic compound, and I have a small typo here. And an ionic compound, you may remember from first year chemistry, is formed between an anion, which has negative charge, and a cation, which has positive charges. So then an example might be like sodium, which is a cation attracted to bromide, which is an anion to form sodium bromide. Oftentimes, you might have remembered that it's composed of metals and nonmetals, and while that's generally true, it's truly just composed of oppositely charged ions. Ionic molecules, or excuse me, that's a misstatement. Ionic compounds do not exist as molecules. So let's go over what a molecule is first and why an ionic compound is not a molecule. So let's just think of something like carbon dioxide. It looks like this, or water, which is H2O, looks like this. And I'll draw some lone pairs just so that they're totally accurate. These are individual molecules, meaning that when we write CO2, that is exactly what it's composed of. When we write water, that is exactly what it's composed of. In these scenarios, they have bonds, which is what I'm pointing to, here specifically a double bond, and here specifically a single bond. And those bonds are where the hydrogen and the oxygen, or the carbon and the oxygen, are actually sharing electrons. And an ionic compound does not share electrons. Instead, it is a transfer of electrons. Ionic compounds are super, super common. Everywhere around you on Earth, there's going to be ionic compounds, even in your body. So what is an ionic compound at the molecular level? So even though I write NaCl, it would be totally inappropriate to say Na is bonded to Cl with a bond like this, where they're actually sharing electrons. And that is totally untrue. Instead, what happens is sodium has 1 valence electron, and chlorine has 7 valence electrons. And for each of them to reach a full orbital, or sublevel, I should say, there's a transfer of electrons. Chlorine, you may remember from last unit, ends at 3p5, and so by doing this, chlorine gets to fill that 3p sublevel, going to 3p6, and we know that that adds a layer of stability. Sodium, on the other hand, starts as 3s1, but before the 3s1 was a 2p6. So when sodium gets rid of the 3s1 to become sodium cation, it's left with 2p6, which is filled. And by both sodium and chloride being able to be filled ions or filled sublevels, that adds that layer of stability. So what does sodium look like? It is actually what we call a lattice. Any ionic compound is a lattice, and a lattice is simply just a repeating pattern. Positive, negative, and this is going to go on for forever. This is why you can't have a molecule of sodium chloride, because not every sample of sodium chloride is a set amount of sodiums and a set amount of chlorides. Instead, it's very similar, where a sample of sodium chloride is instead a ratio of sodium to chloride ions, specifically in a 1-to-1 ratio. A great way to remember what the word lattice means is think about, at Thanksgiving, if somebody makes an apple pie, oftentimes they're going to put a grid on top of the apple pie. Since you're in AP Chemistry, if you see that grid, instead of calling it a grid, it's actually just called a lattice. That is a more accurate term of what goes on top of many types of apple pies. Okay. The actual particles of sodium chloride aren't molecules, as we've said. Instead, they're called formula units. So what is a covalent compound? We've kind of already talked about it, but a covalent compound at its core is just when electrons are actually shared. And it turns out that when electrons are shared between two atoms, it's likely due to a small difference in electronegativity. If I think about the electronegativity of chlorine, I believe it's 3.0, and sodium, don't quote me, I don't know this off the top of my head, but I believe it's 0.7. That's quite a big difference. That's a difference of 2.3. And so chlorine doesn't share electrons with sodium. Instead, it takes an electron. So what if we go to something like this? Oxygen's electronegativity is 3.5, and so is another oxygen's. And at this point, I don't expect you to have those electronegativity values memorized. But oxygen can't steal electrons from another oxygen. They have the same strength or attraction to electrons. Similarly, oxygen is 3.5 and hydrogen is 2.1. Although there is a difference in electronegativity here, oxygen only hogs electrons from hydrogen. It doesn't actually steal electrons. When this happens, you might remember from first year chem that this is called a polar bond, which could result in a polar compound. So there's different tests that we can have to see if we have an ionic compound or a covalent compound. The first is that because ionic compounds are composed of really large charges, meaning full charges instead of like partial charges, they're going to have very strong attractive forces. This is why if you take sodium chloride and you put it on a skillet and put it on a range or a stove, you're just going to have hot salt. You're not going to have melted salt. You're going to have to get it increasingly, like abnormally hot, and I don't think a normal stove is going to be able to melt salt. That's because the attractive forces are so strong. On the flip side, when we have covalent compounds, they have weaker attractive forces. These weaker attractive forces means that it's easier to break the attractive forces. It requires less energy. Surely you know that if we put water on a stove and we turn it up hot enough, we're going to have water go from liquid to gas. And in that transition from liquid to gas, we are breaking the attractive forces between the water molecules. So here are the tests that we can do. The first test is we can test the melting point. Ionic compounds have high melting points. Covalent compounds have low melting points. A really common test is that we can conduct electricity or see if a compound will conduct electricity. If it conducts electricity as a solid, it's not a compound, but instead we would just call it a metal. We probably know this. Many of the wires in the walls of this classroom or the walls of your home probably have copper in them. Copper is a great conductor, but copper is not a compound, but instead just an element. So what if our compound does not conduct electricity as a solid? What we can do is we can try to dissolve it in water and test the conductivity. All ionic compounds dissolve in water at least a little bit, whereas only the polar compounds dissolve in water. If the ionic compounds dissolve in water, they're going to produce ions, and that's going to allow an ionic compound to conduct electricity. Polar covalent or non-polar covalent, so essentially just covalent, never produce ions, and they are not able to conduct electricity. So let me go over something that you've probably heard about. Let's say if you went home and you took a bath, it's probably not wise to charge your phone, charge your laptop, have a toaster, whatever you want to say that's silly, in the bathtub. And you might say, oh, that is because water conducts electricity. And once you say that statement, you are wrong. As we see up here, water is a covalent compound, and covalent compounds do not conduct electricity. So why would it be that tap water or bath water could conduct electricity? Surely you know that the water out of the tap is not pure water, 100% pure water, I should say. And so it's going to have minerals in it. What are some of the minerals in water, you may say? And it's going to be calcium ions. It's going to be iron ions. And because we're going to have ions in our tap water, that's going to allow the tap water to conduct electricity, which is why you should not take electronic devices into, the bathtub or into the shower. The last thing in these notes is that compounds that have, some compounds have ionic and covalent character, and I would just want to show you some of them. I don't think that this is a huge emphasis in the world of AP chemistry, but it is something that can exist. So for example, here I have potassium sulfate. Even though we write K2SO4 as such, and it's very simple, At the molecular level, there's a lot of things going on. So for example, sulfate is composed of sulfur and oxygen. Sulfur's electronegativity is 2.5, whereas oxygen is 3.5. And so that is a small difference in electronegativity. And so those sulfur and oxygen atoms, they actually share electrons. And that's why we see actual lines between them, which represents the covalent bonds. On the flip side, I believe the electronegativity of potassium is something like, oh gosh, I don't remember off the top of my head, maybe like 0.5. This is a huge difference in the world of electronegativity between these, and therefore this forms what's called an ionic bond. And so at the macroscopic level, we may see the ionic bond of -2 for sulfate, +1 for a potassium, and +1 for another potassium, and this pattern repeating for forever, so on and so forth. But if we zoom in on this -2 of sulfate, this is what we see, the actual sharing of electrons. And so it is possible that something could be ionic and covalent in terms of its character.